Same idea as the last hypothesis test, where you don't really need to worry about the assumptions because these things have to be accounted for in the setup if you're doing a project, or the framework of a question if I ask you on a test. Right? The key difference between this type of hypothesis test and what we just did is that this one is related to means. All right? So we're talking about averages instead of proportions. So a mu instead of a p. All right? So the reality is that you're going to see a lot of similarity, like a great deal of like it'll seem redundant. That's how much similarity there's going to be from one hypothesis test to another, but there will be slight differences here and there that distinguishes one type from another. All right. Our only goal here really is to be able to learn how to interpret what the p-value in a hypothesis test tells us, right? Because I keep going back to this: medical journals, engineering journals, whatever. When you're reading an article, my wife's mother is a nurse, and so every now and then I'd go over to her house and I'd see the whatever publication she'd get in the bathroom, and I'd say, oh, let me thumb through this. And so, what else was I going to do? So I would thumb through it, and I would see like a statistical analysis in there. And actually more than one. There was a ton of them, because it's always like some sort of way to educate individuals, like professional development. So people want to stay abreast of the comings and goings in the world of medical science, and so the journal gives that information, and so there's a lot more information than maybe a person might be interested in accessing, but the writer of the article wants to have that information be accessible to all. So there's the abstract that you can read. Then there's the statistical analysis if you're more interested in that, but there's a little something for everyone. And so the thing I was interested in is at the very end, it would say something along the lines of, a study was conducted at the 0.05 significance level to test a claim that there is a significant decrease in blood pressure related to this medication. And then it would say that with a p-value of whatever, there is sufficient evidence to conclude that, and so it's all there, everything that we're learning, but it's stuff that you kind of gloss over pretty frequently. Like if you've actually read one of those articles, you probably just kind of glanced past that stuff, just looking for, does the medicine work or not? And so now you'll have more of a trained eye. You can look at that and say, oh, okay, it was a study that was conducted appropriately, right? Because we've seen all these medications that are recalled, and now you have the personal injury lawyers that are like, well, if you took this medicine and developed a heart defect, come on down and we'll get you some money before you die, whatever. It's like terrible stuff, but that's the kind of thing that maybe you can pick up if you have a little bit of knowledge of, a simple thing. I mean, I'm oversimplifying it. Like, what's a p-value? Now that you know that p-value, even though it proved that the medicine was effective technically, and maybe it wasn't a very, very strong p-value. Maybe you could say, okay, it barely made the cutoff. It barely made the criteria. And so now you're not going to be shocked 5-10 years later when that medication is recalled. All right? So that's the importance of stuff like this. So anyway, looking at the structure of it, null and alternative hypotheses, same. Level of significance, same. Criteria for rejecting the null, same. Conclusion sentence, same. Only thing that's different is the type of test that we're going to use. All right, so we are using a t-test. All right, it's actually short for a student t-distribution. So the person who created this, I mean, there's a story behind it, but basically the individual who created this didn't want their name out there, so they just said, just call me student. So it's my t-test, but just call me student. Don't use my real name. I think he kind of he figured that many years later, there would be people, sitting in a Saturday morning stat class thinking to themselves, who's this SOB who created this? And he just didn't want to have his name on it. And I respect that. Yeah. Anyway, I made a word problem out of this, and it sucked, but I did it. Like 16 years ago. The time it takes for students who drive to school on a daily basis to exit the school from their 8th period class, this is when I taught in a high school that only had 8 periods, start their car and exit school grounds approximates the normal distribution. Just a little background that maybe you care about, maybe you don't. If you're doing a project, then you definitely want to start caring about stuff like this. As my motivation behind doing this was, I was always getting stuck behind the buses when I was trying to get out of the school. And the buses were getting stuck because the seniors who were drivers were casually making their way out to their cars and casually cutting in front of buses and slowing up traffic. And I want to say, do they want to get out of here or what? Let's go. So I sat there in a lawn chair and a stopwatch, and I did it. So on February 3rd, 2003, that's when I kind of was at my limit. That's when I did it. Teacher had nothing better to do, timed a sample of 45 student drivers. Actually, I did have something better to do. That better thing to do was actually try to go home. I also bailed on my, the last 10 minutes of my 8th period class to get started on this process. I was like, here's a worksheet. Enjoy the rest of your day. I'm going outside. And so that was a thing. And so, the average time it took for them to leave was 5.7 minutes with a standard deviation of 2.1 minutes, which I thought was absurd. Right? Now, if you don't work with data often enough and contextualize that data, it's hard to determine what's a large number and what's a small number, right? I think we've all been in the situation, like elementary school, middle school, whatever. You raise your hand, you raise your little hand, and say, "Can I go to the bathroom?" And the teacher says, "Yeah, you got 2 minutes." And you're like, "How am I supposed to do anything in 2 minutes?" And then you go, you do it at whatever rate you think is the normal rate, and you come back and you still got 45 seconds to spare. You're like, wait, it only takes 1 minute and 15 seconds to do all that? That's crazy. Man, I had 45 seconds. I could have washed my hands. This is incredible. I could take my time. So 5.7 minutes, it may not seem like that's an absurdly large number for students to exit the school grounds, but the 2.1 was even the more alarming thing. Right? So you're looking at already a large number for students to get in their car and start the process of leaving, and then a 2-minute variation related to that. Right? So that it's in my mind at the time significant. All right? So we overuse the word significant in real life because it's a cool word. We use it a lot. Right? But statistically, it means that there has been a successful outcome related to a hypothesis test. All right? So that's what we're going to do here. We're going to, my perception was that there's a significant relationship. Now I want to see is there a statistically significant relationship? All right. So I'm going to go through my information here and see what I got. I have 45 student drivers. I have a mean. All right. So I have one population mean. So that's telling me it's a t-test. All right. Now that wouldn't necessarily tell you that it's a t-test, but now that I've told you that one population mean corresponds with t-test, from now on, you'll know. All right, because that's the idea. This is weird. Where'd everything go? Oh, that's so strange. Whatever. So stat test option 2. The only quirky thing about this particular hypothesis test, and it's really not that quirky, it's just it gives you a couple options. You could input data or you can input statistics. So if I gave you a raw list of data, so I had 45 student drivers, I determined the mean to be this and the standard deviation to be that. I could have just gave the list of 45 student drivers and the time that it took for them to leave the school grounds, and then let you type that into your calculator. The calculator accepts that. Like if you type your information into a list and then select data here, it'll run the numbers for you. All right, but that means that you'd have had to type in 45 values, right? Which is not something I'm interested in having you do. So we're just going to work with stats. All right, the mu sub o, x bar, sx, 4500. That's, well, 4500 is that's held on to from the last hypothesis test that we did. We'll have to change that. But these numbers here, they're all related to the problem. So we could pull this out of the word problem in some way, shape, or form. So if you get jammed up and think like this is a one prob z test, then you start looking at the information that you have, you'll realize that you have too much information, so it couldn't possibly be that. You hit stat test option 2. It says t-test at the top. And it says stats is highlighted. And you hit enter. Right, yeah. So it's in this menu that we have to start really putting our information in. But let's, before we do that, determine what our null and alternative hypotheses are going to be. All right, so HO and HA. Use a 0.01 significance level. All right, I'll chuck that in there too. Alpha is equal to 0.01. To test the claim that the mean time it takes for students in general to go through the above routine, all right, a lot of words, is actually greater than 5 minutes. So mean greater 5. All right, a lot of words, but that's really what it boils down to. All right, a greater than symbol. Does that correspond with a null hypothesis or an alternative? Alternative. All right, so I'm going to say mu, if I could properly produce a mu, mu greater than 5. All right. The null hypothesis only involves an equal sign. That's our default. Same ingredients, just with an equal sign. So another mu, another 5, but this time an equal sign. All right, so I would annotate this, but I would be annotating it exactly the same way I did the last hypothesis test. All right, the mu's are going to be the same. The 5s are going to be the same. The greater than comes from the problem. The equal sign is always there because that's how it is for a null hypothesis. All right, the number 5. That's going to be our, instead of p sub o like the last hypothesis test, this is going to be our mu sub o. Our initial mu, our default mu. All right. And the only reason I know I need that is because when I go into the t-test menu in the calculator, it asks me for a mu sub 0. All right, so I know I got to put a number in there. It also asks me for an x bar, sx, and 45, I keep saying 4500, an n value. All right, so I go into my word problem, and I take a look at the information. It tells me that there is a sample of 45 drivers. All right? That's a number of individuals. So that's an N. So a sample of 45 drivers. The mean for that sample, defined as a sample mean, was 5.7. The standard deviation for that sample, S, is defined as 2.1. So everything we need is given in this word problem.
That's for SS, right?
Yeah. Either way. So in my menu, I'm just going to type this stuff in. I'm going to put in a 5 for mu sub 0. I'm going to put in a 5.7, a 2.1, and a 45. Now again, the theory behind this is that, because you might look at it and say, I mean, the question's asking us, is the mean greater than 5 minutes? You look at it and say, well, yeah, it's 5.7. That's greater than 5. We're done. Why are we doing this? This only talks about the sample. We know that these 45 students took 5.7 minutes to leave school grounds. How does that project out to the population? That's what this technique shows us. It shows us the probability, or it gets at the probability for the entire population following that same distribution. All right. So let me get this in the notes. Oh, it worked this one time. And then just hit enter on calculate. And again, we're only pulling the p-value out of this. All that other information is useful, just not for us. All right. So the recurring question is always going to be, how does the p-value relate to the alpha value? So I'll write the statement again, because this is how you draw your conclusion. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is less than alpha, we reject the null hypothesis. So my p-value, I'm going to round it, 0.0152. That's the p-val. The alpha value is 0.01. So I just want to see, is it true that, I'll put the less than symbol in there, but I want to know, is it true or not? Is 0.0152 less than 0.01? No. It's greater, yeah. So not true. Therefore, do not reject the null hypothesis. All right, so I don't reject the null hypothesis because this is not a true statement. And again, you could use the test menu on your calculator to figure it out. I mean, because this one I didn't think you needed it because the decimals aren't that bad, but sometimes they get a little funky, and you know, worst case scenario, maybe you just want to have a little bit of a safety net, where you say, yeah, I'm pretty sure, but why tempt fate? You know, so if that's the case, then what you would do, again, it's very rare that people actually like using this. I don't mean to like disparage this process, but it's just not very popular. So vars, statistics, test, 1. That brings up the p. But you could actually even just type it here because it's a simple enough decimal. Second math, option 5. So exactly the same way we did it on the previous, for the previous problem. And then put in your alpha value, which is 0.01. Hit enter.
Test was 2, right?
Say it again.
After test was 2, option 2.
Option 1. Yeah, it's the one that says P. And we get a 0 as a result, which is false. All right, so it's confirming what we said before. Okay, so that's good news. I mean, that's what we thought, and so it's definitely a good thing. Keep having these moments where I want to say something and then I forget what I'm going to say. Oh, yeah, it had to do with the alpha value. So now this became kind of this problem sort of took on a life of its own, because when you conduct a study, I mentioned before, you go into it sometimes not even knowing what your alternative hypothesis is going to be, what your question is going to be, because you don't really know what the relationship is. So this is different because I walked into this study being like, these kids don't want to get out of school for some reason. They're casually getting their way to get, and which was surprising because I thought, you know, bell rings and there's a mass exodus. Everybody wants to get out of there, but they're like cruising their way out. So I was surprised by this outcome, but you still go into it with an open mind. But I always had the question in my head that the average time is going to be lengthy, that they're taking too long to get out of school, right? They're not showing any urgency, right? So, and that would affect policy change because the administration at that school at that time, they designated student drivers go first, then buses, right? What I was trying to say is let the buses go first, make the students wait because they're not rushing to get out of here anyway. Okay, so there's kind of an uproar over that, but I tried to verify statistically. So if I look at this as an alpha value of 0.01, we get a do not reject. But if my alpha value, which I selected, if my alpha value was 0.05, it would have rejected. I would have been able to reject the null hypothesis. All right, so it really does depend on what you use as your alpha value. Right? So statistics is very malleable that way. So you could actually have the same data set as somebody else, run the same statistical analysis as somebody else, but come up with the exact opposite conclusion. Right? I tried to make it as strong as possible by using the most really challenging alpha value, right? Because if you reject for a 0.01, you reject for all the others, right? But I could have also, I mean, that 5-minute mark was something I chose arbitrarily also. If I said they're taking more than 3 minutes to get out of school, I could have gotten a rejection with any of these numbers. Okay, so there's a lot of wiggle room here to kind of define it based on the way that you want it to go, right? Which makes it really suspicious. You know, whenever you see the results of a statistical analysis, you really have to kind of develop an eye for it and know when people are trying to BS you and when they're not, right? Because your first question should be, why that alpha value? Why not that alpha value? You know, because most of the time, the selection of the alpha value is what determines whether or not a study will be significant or otherwise. All right, but in this case, it's saying it's a do not reject the null, which means that we're going with the null. The null is the good one. The alternative is the bad one. So based on these parameters, that's the only conclusion we can draw, but now we got to write the whole conclusion. Now, if I wasn't like yapping away up here, you'd get a real sense of how quickly this process goes, because really it's just a matter of identify the test, pop in the values, get the p-value, start writing your conclusion. Like all of this work that if I looked at the clock more carefully at probably like 5-10 minutes, maybe more. We're talking about like 30 seconds, 45 seconds of work. All right, so it's not as lengthy of a process as I'm making it seem, but I'm not doing that on purpose to torture you or to kill time or whatever. I'm doing it so that you can hopefully have a somewhat of an intuitive understanding of this, so that if you do try to do the project, you can at least know what the hell you're trying to do. All right, that's the hope anyway. So don't hate me for this. Yeah, I'm copying and pasting. So if you do a project, you wouldn't have to handwrite your conclusions. And also, just please understand, projects are harder for me to grade. They're not easier. So like me not discouraging, but encouraging you to do a project in no way makes my life easier. It's gonna be better if you do a project. So there is sufficient evidence to reject the claim that the population, not a proportion anymore, mean. Yeah, we're getting going on it. I copied and pasted it, and now I'm editing. So some parts of this are going to get adjusted, because the truth's going to become false in a second. And also, it's going to be insufficient evidence, so I got to make that adjustment also. So insufficient evidence, so I'll change that in a sec, to reject the claim that the population mean. Now, when you're stating your null hypothesis and alternative hypotheses, you can feel free to paraphrase it a little bit. On the last one, I was kind of being a wise guy a little bit, but like chose apples as the most delicious fruit. Like we wrote that like 4 times. That kind of sucked. But you can figure out a way to paraphrase it to get the idea across. So here it's, what are we talking about? Test the claim that the mean time it takes for students in general to go through the above routine. So the population mean time it takes students in general to go through the above routine, no, I don't like that. So what we could say is there is insufficient evidence to reject the claim that the population mean time it takes students to leave school. I mean, you're still writing, but you're kind of figuring out a way to get the point across without writing as much. So the places where you have freedom to kind of adjust the template would be basically the colored stuff. So when you're describing what the null and alternative hypotheses are. But the part where there is insufficient evidence, there is sufficient evidence to reject the claim that blah, 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 that has to be as is. The first sentence always is talking about the null hypothesis. The number of times I've seen people write a conclusion where they say there is sufficient evidence or insufficient evidence to reject the claim that the time it takes students to leave school is greater than 5 minutes. I mean, it's terrible. All right, follow the template, you will not have a problem. All right, even if I'm reading it and I'm like, whoa, that is grammatically the worst sentence I've ever seen. It's following the template, you're good to go. Is 5 minutes. Now this is only true at the 0.01 significance level. Because if it was actually at the 0.05 significance level, it would be sufficient evidence. Therefore, the claim that it takes, you can simplify it now because we've already kind of talked about what it is, that it is more than 5 minutes. Now that's going to be false. little spacing issue here. I mean, I'll get over it almost immediately, but I should at least try. Move it over, smidge Ruski here. The lane? No. Oh, hello. Yeah, well, that's something. Whatever. I've lost interest. So there is insufficient evidence to reject the claim that the population mean time it takes students to leave school is 5 minutes. So that statement establishes what the it is in the second sentence. All right. Therefore, the claim that it is more than 5 minutes is false. All right. So you can see here, just like on the last one, that insufficient corresponds with false, just like sufficient corresponded with true. All right. But we could have streamlined it a little bit in the last one, but I was kind of trying to get a point across. So when we said in the second sentence, therefore, the claim that apples, population proportion of apples, people who selected apples as being the most delicious fruit is more than 0.5. We could have said, therefore, the claim that it is more than 0.5 is either true or false, right? So things start getting a little bit more streamlined as we go on, because we start moving away from having to discuss the theory over and over again, and we get more into just like, let's get it done, all right? So that's part of the fun, I guess. So that was page 53.